Hey everyone, welcome back. Ready to dive into something pretty cool.
Definitely.
Today, we're talking all about radio waves.
Oh, cool. Radio waves.
Yeah, but we're going way beyond just turning on the radio. We're going to uncover the kind of hidden world of radio that's all around us.
Yeah, it's everywhere, isn't it?
It really is. So I was looking at this Wikipedia article on radio, and it got me thinking about the early days of radio, before we had smartphones and Wi-Fi and all that. Did anyone even set out to invent radio, or did it just kind of happen by accident?
That's a really good question. What's so interesting is that so many big discoveries, they actually come from, pure science, not from someone trying to invent something specific at all. It's true. Take Kyra Kurtz, for example. He wasn't setting out to build a radio when he started experimenting with electromagnetic waves back in the 1800s.
Wait, so what was he doing?
Well, he was trying to prove a theory, actually. James Clerk Maxwell's equations, which predicted that these waves existed. So Hertz built this device that could actually generate and detect them.
Wow.
Yeah. So he basically proved Maxwell right. Huge moment for physics.
So he was more interested in, how the universe worked than actually sending, a text message or something.
Exactly. But you see, by doing that, he actually laid the foundation for, everything we're going to be talking about today. Radio communication.
Wow.
And what's interesting? It took a while for things to move beyond just basic messaging, too.
Oh, you mean like those old-timey telegrams?
Exactly.
With the dots and dashes. Oh, I can't even imagine waiting for a message to come through one letter at a time.
I know. It's such a far cry from instant messaging and everything we have now. And what's really surprising is that era of what they called wireless telegraphy, it actually lasted for a really long time.
Yeah.
We're talking almost 2 decades.
Wow.
Yeah. It wasn't until they developed continuous wave technology that we could even think about transmitting voices and music.
So for 20 years, it was basically a global network of Morse code.
Yeah, pretty much.
That's why.
It really goes to show you how innovation, sometimes it's a very gradual thing.
Yeah.
Each new thing builds on the one before it. But of course, once they had that continuous wave technology, things really started to change quickly.
Yeah, I bet that 1920 election broadcast, that was the first commercial one ever. That had to be a huge deal. Can you imagine hearing the election results come through, the airwaves for the first time?
Oh, I know. That's a real historical moment right there.
Totally.
And to think, it all goes back to these invisible waves that Hertz first, experimented with. Now, when we talk about radio waves, it's really important to remember that we're actually talking about a whole spectrum of different frequencies, okay?
Yeah.
Each one has its own, unique properties.
Oh, okay, so it's not just one size fits all.
Not at all.
So what kind of, what kind of neighborhoods are we talking about on this radio spectrum? What's out there?
Okay, well, think of it like a piano keyboard, okay? Each key on that keyboard, that's like a different frequency band. And just each key makes a different sound, right?
Yeah. Each band, it's got its own special characteristics.
Okay, so it's not just about the wave itself. It's also about tuning into the right spot on the dial, so to speak.
Yes, sir.
So what are some examples, then, of these different bands and what makes them unique?
All right, well, on one end of the spectrum, you've got what are called extremely low frequency waves, or ELF waves.
ELF waves, okay.
Yeah, and these are incredibly long waves. And get this, because they can actually penetrate water, they're used for submarine communication.
Hold on, submarines use radio waves.
They do.
I thought they were underwater. How does that even work?
Well, that's the thing about these ELF waves. They can actually travel through hundreds of feet of seawater, which allows, communication with submarines even when they're deep down. That's incredible. So you've got messages traveling from the depths of the ocean and then all the way up to what, satellites in space? What kind of frequencies are we talking about for something like that?
Yeah, you're right. As you go higher up that spectrum that we were talking about, you hit the microwave band.
Okay.
And those frequencies, they're perfect for satellite communication because they can easily go right through the Earth's atmosphere.
Wow. Okay, so we really are talking about a huge range of stuff here.
Huge.
Saying radio is starting to feel like saying transportation, It's everything from a bicycle to a supersonic jet.
That's a great way to put it. And just like with transportation, understanding all the different, let's call them vehicles on the radio spectrum, is key to understanding how we actually use and navigate this incredible technology.
Yeah, and, it really highlights just how diverse radio waves are, and we've only just kind of scratched the surface. Like last time we were talking about those early radio pioneers, they started with Morse code messages, which is a long way from how we use radio waves today.
Oh, yeah. It's amazing how far we've come. I mean, I can walk around my house talking to my smart refrigerator while I'm listening to music streaming on my phone, all thanks to radio waves. So how does that even work?
Yeah.
It's not like we each get our own personal frequency, right?
You're right. That would be completely chaotic. What actually makes this possible is a really clever technique called frequency reuse.
So imagine a city, and it's divided into this grid, right?
Okay.
Each square on that grid, that's a cell. And then each cell has its own cell tower.
So instead of like one giant antenna trying to reach everyone, we have all these smaller towers covering their own little areas.
That's it. And here's the really cool part. Each cell can actually use the same set of frequencies as all the other cells without interfering with each other.
Wait, really? How?
As long as the conversations are taking place in different cells, they can all be happening on the same frequency at the same time.
So it's kind of like if you imagine having a bunch of conversations happening in the same room, but each conversation is in its own little soundproof booth.
Exactly.
So you can hear the people in your booth perfectly, but all the other conversations are blocked out.
That's a great way to think about it. And this whole idea of frequency reuse, it's not just for cell phones either. It's the backbone of tons of wireless technologies we use every day, things like Wi-Fi and Bluetooth.
Wi-Fi, Bluetooth, it's so funny those are just everyday words now, right? We don't even think about it. It's easy to forget that they actually use the same basic technology as those old radio transmissions.
It really goes to show how one fundamental discovery can be applied in so many different ways. But let's shift gears for a minute and talk about something a little different, RFID. You've probably seen these little radio frequency identification tags, maybe without even realizing it.
RFID, you mean those little stickers you see on products sometimes?
Those are a great example.
I always wondered what those were.
So those tags, they're essentially tiny little microchips, and they've got a little antenna attached to them.
Okay.
And here's the really interesting part. They don't actually have batteries.
No batteries.
Yeah.
So how do they, like, transmit information if they don't have a power source?
Well, that's the clever part. When the RFID tag gets close to a reader, it can actually pick up enough energy from the reader's radio waves to power itself up just for a moment.
What?
Yeah. And that little bit of energy is enough to power up the tag's microchip. And then it uses that power to send its information back to the reader.
So the tag is basically borrowing a tiny bit of electricity from the reader to send a quick message.
That's a great way to put it. It's like a little wireless energy transfer.
That's wild. What kind of information can these things even hold?
All kinds of stuff. It could be a unique ID number, information about the product, tracking data. It really varies. That's why they use RFID in so many different things like managing inventory, library books, even those contactless payment systems we were talking about.
Oh, that's right. It's like a secret little handshake between the tag and the reader, totally invisible to us.
But it makes all sorts of things possible.
Exactly. And the seamless way that radio technology just blends into our lives, it's really fascinating. But it also brings up a really important question. With all these devices all using radio waves, how on earth does anything ever work? How do they not interfere with each other constantly?
That's what I was wondering. It's like if everyone is broadcasting on different frequencies, wouldn't the airwaves just be a jumbled mess? It'd be like trying to have a conversation at a rock concert. You're exactly right, and that's where regulation comes in. Remember we talked about the ITU, the International Telecommunication Union, earlier?
They're like the air traffic controllers for the radio spectrum, right?
Exactly. They're crucial for preventing all that interference by making sure that specific frequencies are set aside for specific applications. They set worldwide standards and basically make sure everything runs smoothly.
So they're kind of the unsung heroes of the airwaves. They keep our wireless world from descending into total chaos.
You could say that, yeah. And it's this careful coordination that allows us to enjoy all the benefits of radio technology without even having to think about it. But speaking of amazing applications, let's talk about radar for a minute. A lot of people associate it with weather forecasting, but it's used for so much more than just predicting rain or shine.
Oh, I've always been curious about radar. It seems kind of magical, like you're sending out these invisible waves to map out the world around you.
It does seem that way. But at its core, it is actually that simple. Basically, radar systems send out pulses of radio waves, and when those waves hit something, they bounce back to the receiver.
Okay.
And then by measuring how long it takes for those reflected waves to travel back, the system can figure out how far away that object is.
So it's like shouting into a canyon and listening for the echo to figure out how far away the walls are.
Exactly.
Very cool.
And just like your ears can tell which direction the echo is coming from, the radar antenna can figure out the direction of those radio waves so it knows both the distance and the direction to the object.
So we're basically giving our technology eyes, letting it see even when it's dark or there's bad weather.
That's a good way to put it. And it gets even cooler. There's also something called Doppler radar. You've probably heard of it in weather reports, right?
Mm-hmm.
Well, Doppler radar can actually tell us how fast an object is moving.
Really? How does it do that? Does it, like, send out faster waves?
Not quite. It uses something called the Doppler effect.
Okay.
So think about an ambulance siren for a second. You know how it sounds higher pitched when it's coming towards you and then lower pitched as it moves away?
Oh, yeah. I've definitely noticed that. It's like the sound waves are getting squished together as it gets closer and then stretched out as it goes away.
You got it. And that same principle, it applies to radio waves as well. With Doppler radar, the frequency of those reflected waves changes a little bit depending on whether the object is moving towards or away from the radar. So by analyzing that change in frequency, we can figure out the object's speed.
So it's like the radar is listening for that change in pitch, even though it's radio waves and not sound waves.
Exactly.
Very cool. What else uses Doppler radar besides, like, weather forecasting?
Oh, tons of stuff. It's used in air traffic control to track planes. Meteorologists use it to study storms. Even law enforcement uses it for those speed trap cameras you see on the highway.
Busted by the Doppler effect. Okay, that's both very impressive and a little bit scary, but speaking of impressive, I've always been amazed by GPS. It's like having a personal navigator in my pocket, which has to be one of the most life-changing uses of radio technology, don't you think? But isn't that more about satellites than radar?
You're right. GPS relies on a network of satellites. But it's all connected, actually. If you zoom out and look at the bigger picture, you'll see how it all comes together.
So we were talking about GPS before the break and how it all kind of ties back into this.
Yeah.
It seems like a big jump, though, going from radar to, like, pinpointing my location on a map.
It might seem like a big jump, but it really comes down to incredibly accurate timekeeping. And there's one really cool thing about the speed of light.
Okay.
Or, well, the speed of radio waves in this case.
All right, you've got my attention. Break it down for me.
Okay, so picture this. Every single GPS satellite that's orbiting the Earth, it has this super precise atomic clock on board.
Atomic clocks, those are, like, really accurate.
Yeah. Oh, they're incredibly accurate. We're talking losing less than a second every 100 million years.
Wow.
And these atomic clocks, they're always transmitting their time signals down to Earth using, you guessed it, radio waves.
So we've got these, like, super accurate time signals beaming down from space. Then what?
All right, so that's where your GPS receiver comes in.
Okay.
It's picking up those time signals from a bunch of different satellites all at the same time.
So my phone is, like, having a conversation with a bunch of atomic clocks in space right now?
Pretty much.
That's kind of mind-blowing when you think about it.
It really is. And here's the key. By comparing the tiny, tiny, tiny differences in the arrival times of all those signals, your GPS receiver can actually figure out exactly how far away it is from each of those satellites.
So the further away the satellite, the longer it takes for its signal to arrive makes sense. But how does knowing how far away I am from a few satellites actually tell me where I am?
That's the magic of triangulation.
Okay.
So by taking the distance measurements from at least 4 different satellites, your GPS receiver can use those to pinpoint your location on Earth with crazy accuracy.
So it's like those, what were those geometry problems we did in school, but, like, on a cosmic scale?
Exactly.
These satellites are drawing these imaginary lines in space, and where they all meet, bam, that's where I am.
That's a great way to think about it. And it all relies on this one crucial fact, that the speed of radio waves is constant. So we know that, and we know exactly when the signals were sent, which lets us calculate those distances and figure out your location.
Wow. From submarines to satellites, it's amazing to think that it's all powered by this one thing, radio waves. It really makes you wonder, what's next?
It's true. And what's so cool is that people are still discovering new ways to use radio waves all the time. Even that Wikipedia article you were talking about before mentioned radio astronomy.
What's that?
Basically, it's like listening to the cosmos, but instead of using your ears, you're using radio waves to detect faint signals from distant stars and galaxies.
So not just using radio waves to find our way around the Earth, but to explore the entire universe.
Exactly.
That's kind of a lot to process.
It really highlights how important radio waves have become for scientific discovery. We're not just, chatting with each other anymore. We're using radio waves to learn about the universe around us.
This has been such a cool journey. We started with the very basics of radio waves, these invisible messengers, and now we're talking about understanding how they impact pretty much every part of our modern world.
And to think it all started with a little scientific curiosity.
It really makes you appreciate those early pioneers like Hertz,
Yeah.
just tinkering around in his lab all those years ago, and look what he helped to create. It really makes you think twice the next time you listen to the radio or connect to Wi-Fi, even just check your GPS. It's all thanks to these invisible waves.
It really is remarkable. And who knows what amazing new discoveries are still out there waiting for us, right?
Exactly. Well, on that note, we'll wrap up for today. Thanks for joining us for another deep dive, everyone.
Thanks for listening.
Remember those crazy wildfires that ripped through California last year? I was just reading that they were fueled in part by, like, the after effects of La Niña.
Oh, really? Yeah.
Yeah, and it got me thinking about El Niño. That whole unpredictable weather thing. You sent us that Wikipedia article on it, the El Niño Southern Oscillation, or an NNSO.
Right.
And we figured, let's really, dive deep into this, go beyond just the headlines.
Yeah, it's pretty amazing how much it impacts, the whole world,
Yeah.
right? And a lot of people, I think, they hear El Niño, they just think, oh, yeah, weather.
Right, exactly.
But it's so much more than that.
It's not every day you hear about, a weather pattern and it's impacting economies and ecosystems and even historical events thousands of miles away. Wild.
Yeah. It all starts with this kind of delicate dance
Yeah.
between the ocean and the atmosphere in the Pacific. So just imagine this. The Western Pacific is usually a good, 8 to 10 degrees Celsius warmer than the East.
Really?
Yeah. It's kind of like if you could just, step out of a sauna, say, in Fiji, and then into a cool breeze in Peru.
Wow.
But you're in the ocean the whole time.
That's a huge temperature difference. What causes that?
So it's this really cool process called upwelling. And basically, just picture it as this, giant underwater conveyor belt. So it's constantly bringing up this cold, nutrient-rich water from the depths. And it brings it up to the surface along the coast of South America.
Huh.
And that's what usually keeps the Eastern Pacific, relatively chilly.
So when we talk about El Niño and La Niña, and then those neutral times in between, we're really talking about, what's happening with that temperature balance, right? Out
Exactly.
in the ocean.
Yeah, it's like a giant seesaw.
Okay.
El Niño's the warm phase.
Okay.
La Niña, the cool phase.
That's it.
And then neutral is, everything's just kind of vibing.
Okay, so let's talk about El Niño then, that warm phase, because that's when things, literally heat up.
Yeah. So basically during El Niño, those trade winds, there's kind of like a giant fan, right? They usually push warm water over to the west. And then it's like someone hit the pause button on the fan.
Okay.
And all that warm water, it surges back towards the east. And it basically blankets the Eastern Pacific in what I like to call an unexpected tropical vacation.
But it's not just the Pacific, right? The whole world feels this.
Exactly. Imagine you toss a pebble into a pond.
Okay.
The ripples, they don't just stay put, right?
Right.
El Niño's kind of like that. The impacts, they radiate outwards.
Mm.
And they influence weather patterns, rainfall, even hurricane seasons thousands of miles away.
It's crazy to think that something that seems so, isolated can have such huge consequences.
Yeah, it really just shows you how interconnected the planet is.
Yeah.
And here's the other thing. It doesn't really follow a schedule. It can appear every 2 years, or it could take a 7-year break just to keep us on our toes. And then even when it shows up, it can stick around for 9 months, 2 years. Who knows?
So if El Niño is this unpredictable guest who shows up and just throws this massive party in the Pacific, then La Niña's got to be the quieter, more predictable one, right?
Yeah, in a way. So during La Niña, those trade winds, they come back from their break, but they come back with a vengeance.
Oh, no.
They're blown even stronger than usual.
Okay.
And they push that warm water back westward. And so that makes the Eastern Pacific even cooler than normal.
And La Niña, it's not just chilling in the Pacific either, though, right?
No, not at all.
Global impacts there, too.
Totally. So, for instance, La Niña is often linked to much stronger hurricane seasons in the Atlantic.
Huh.
You remember a few years back, all those devastating floods in Pakistan, I think it was 2010?
Oh, yeah.
La Niña's fingerprints were all over that.
Wow. So it's like a global domino effect. But wait, the article you sent mentioned something called EMSO variations. Does that mean that there's different types of El Nino and La Nina?
Yeah, exactly. Okay, just like there's different types of coffee,
Okay.
each with their own like flavor profile.
Yeah.
Ianso has variations like Ianso Madoki and Ianso Costero, and they all have their own like little quirks, and their impacts are different.
So it's not just about warm or cool phases, but also like where those warm or cool zones are the most intense.
You got it.
Interesting.
So like, for example, Ianso Madoki.
Okay.
Sometimes it's called Central Pacific El Nino.
Okay.
It involves warming in the Central Pacific
Okay.
rather than in the Eastern Pacific.
Okay.
And guess what? That variation is linked to more hurricanes making landfall in the Atlantic.
So understanding these different ENSO variations is like having like a secret decoder ring for predicting global weather patterns almost.
Kinda, yeah.
This is incredible. But there's always a but, right? With climate change and everything, does a warmer world mean that we should expect like more frequent or more intense El Niños?
That is the million-dollar question.
Right.
And honestly, the science is still kind of up in the air about it.
Okay.
There really isn't a consensus yet on whether climate change will cause more El Niños or whether they'll be more intense.
So no need to like stock up on sandbags just yet.
Not necessarily, no.
Okay.
I mean, we don't know if El Niño will become more frequent, but we do know that climate change is making the impacts of these events much worse. Droughts, floods.
Okay.
Think of it like this. Climate change is cranking up the volume on like an already really powerful sound system.
Okay.
The music might stay the same, but the impact on your eardrums
Oh, yeah.
definitely amplified.
Okay, so that leads to a pretty crucial question, I think. What does all this mean for, like, everyone? More specifically, what kind of El Nino and La Nina impacts should we, like, be prepared for in different parts of the world?
Yeah, that's a great question. And unfortunately, it's not like a one-size-fits-all answer.
Right.
The impacts are really different depending on the region.
Let's break it down then. What about Africa? How does ENSO affect this massive continent?
Well, Africa's a great example of how like different El Niños impacts can be. So in southern Africa, El Niño usually means things are going to be drier,
Okay.
higher risk of drought. And then La Nina kind of flips the script, brings more rain than usual, sometimes even floods.
So it's like feast or famine for southern Africa.
Pretty much, yeah.
Depending on, which way the ENSO pendulum swings, I guess. What about other parts of Africa?
So East Africa also gets that seesaw effect, but the timing's different.
Okay.
El Niño tends to bring more rain during their short rainy season, which is like October to December.
Okay.
But La Nina brings more rain during their long rainy season, March to May.
Wow, it's complicated.
Yeah, it's all these regional weather patterns all kind of interacting with each other.
Yeah, it shows you that you can't just look at the global trends, right?
No.
You got to look at the regions too. Okay, let's move over to Asia then.
Okay.
How does ENSO affect things over there?
Asia's really interesting when it comes to ENSO
Okay.
because it's so big, right?
Yeah.
So many climates. So the impacts, they're all over the place.
Okay.
But one thing that's pretty consistent is that during El Nino, the monsoon season in Southeast Asia, it kind of gets suppressed. So things are drier than usual.
And that region relies so much on those monsoon rains for like agriculture and everything.
Exactly, yeah.
That's going to have some pretty big consequences.
Oh, for sure. We're talking potential food shortages, economic problems, higher risk of wildfires, especially in Indonesia when there's a strong El Nino.
Oh, wow. Okay, so then La Nina, I'm guessing that brings more rain than usual.
Yeah, often.
Yeah.
Heavier monsoon rains. That could be good for agriculture, but it also often leads to some really bad flooding. So it's a trade-off.
Always a trade-off.
Okay, well, speaking of floods, what about Australia?
Yeah.
They know a thing or two about extreme weather there.
They do. Australia is actually one of the most ENSO-sensitive continents in the world.
Really?
Yeah. During El Nino, it tends to be much drier and hotter,
Okay.
which of course means way higher risk of bushfires, especially in the southeast. Those were some crazy bushfires back in 2019, 2020.
Yeah.
The ones that just seemed to burn forever, were those influenced by El Nino at all?
So they weren't solely because of El Nino, but it definitely played a role. Those fires were made worse by something called a positive Indian Ocean dipole. Basically, that just means there's a band of warmer than average water in the western Indian Ocean.
Okay.
And that tends to happen at the same time as El Nino.
Oh.
So it just amplifies those hot, dry conditions that bushfires love.
like a perfect storm of bad circumstances. And then La Nina swings by. What happens then? Does that, like, bring some relief? Or is it just more extreme weather?
Usually it's the opposite. Think torrential rains, flooding.
Okay.
Those terrible floods in Queensland back in 2010, 2011, those were largely because of a strong La Niña.
So poor Australia, stuck on the ENSO roller coaster.
Pretty much.
All right, well, let's shift gears geographically again. Let's talk about North America. What kind of impact does ENSO have closer to home?
So North America's a little different. The impacts, they're more regionalized.
Okay.
El Niño usually brings warmer winters to a lot of Canada.
Okay. Which could be a good thing, right?
Yeah, I mean, it sounds nice, right?
Yeah.
But those warmer temperatures can actually be a problem. Less snowpack, which impacts everything.
Yeah.
Water resources, skiing.
So Canadians might enjoy the break from the cold, but they might not enjoy fewer ski trips.
Exactly.
All right, well, what about the U.S.? How do things shake out there?
So the southern U.S., especially California, tends to get a lot more rain during El Niño, which, again, could be good, could be bad, could help with droughts, but it can also cause flooding and mudslides.
Finding that balance, always tricky.
Yeah.
And what about La Niña in North America? What should we expect?
So La Niña often brings those colder, snowier winters to the Pacific Northwest and parts of the Midwest.
Okay.
And then the southern U.S. tends to be drier.
Okay.
Plus, we touched on this earlier, La Niña can make those Atlantic hurricane seasons much more intense.
Right.
Bad news for anyone living along the East Coast or the Gulf Coast.
So white Christmas for some, heightened risk for others. We've talked about Africa, Asia, Australia, North America. What about those Pacific Islands?
Yeah.
They're right there in the thick of it.
Oh, yeah. They're basically ground zero for El Niño and La Niña. And they get hit with a lot. Different rainfall patterns, higher risk of drought, rising sea levels, coral bleaching.
Ah, yeah, the coral bleaching. That's a big one, isn't it? I mean, coral reefs are already struggling with climate change.
They are.
How's ENSO making things worse?
So El Niño, it often triggers these big coral bleaching events in the Pacific.
Okay.
The warmer waters, they stress the corals out,
Okay.
which makes them do something kind of sad. They expel the algae that live in their tissues. And the algae, those are what give the corals their beautiful colors.
Oh, all right.
But they also give them food.
So they need those algae.
Yeah, they need them.
Yeah.
So without the algae, they turn white,
Right.
and they're way more likely to get sick.
It's like adding insult to injury, right?
Yeah, it's tough.
Okay, well, we can't forget about South America. Right there on the front lines of the Pacific. What's ENSO doing there?
So South America, especially the West Coast, that's where you see some of the most intense El Niño impacts. The coastal regions of Peru and Ecuador, they're usually pretty dry. But during a strong El Niño, they can get hit with massive amounts of rain. We're talking widespread flooding, landslides, fisheries get disrupted.
I remember seeing pictures of that on the news a few years ago. Whole villages just gone, buried in mudslides. It's hard to even wrap your head around it.
Yeah, it really shows you the power of ENSO.
It does. And it sounds like those same areas that get flooded during El Niño are dealing with severe droughts during La Niña.
Often, yeah.
Just a never-ending cycle of extremes.
It's true.
This is really driving home the point that ENSO isn't just about the weather, right? It's shaping lives. Yeah. Landscapes all over the globe. But it's not just a modern problem either, is it? This whole ocean atmosphere dance, it's been going on for a really long time.
Oh, absolutely. We're talking a very long time. We've actually found evidence of El Niño events going back at least 300 years.
Wow.
Just from historical records. And some scientists think it's been influencing the Earth's climate for thousands of years, maybe even longer. There's even evidence in geological records suggesting that ENSO has been around for a very, very long time.
That's wild. So this isn't just some like blip on the radar of Earth's history. This is like a fundamental rhythm that's been shaping our planet for who knows how long.
It's true.
Okay, well, since we're talking about understanding the past, you mentioned some pretty interesting connections between El Niño and some major historical events. What were those about?
Yeah, there's more and more evidence that El Niño's reach goes way beyond just, like, the weather. So, for instance, some researchers think that there was a really strong El Niño back in the late 1700s.
Okay.
And that it actually led to, like, really bad harvests in Europe.
Huh.
And that this lack of food might have even played a part in, get this, the French Revolution.
Wow. So El Niño might have helped topple a monarchy. That's kind of a crazy thought.
It is, right?
Okay, but there were other examples too, right? Something about famines in the 1800s.
Yeah, so in the 1870s, there was this incredibly strong El Niño.
Okay.
And it caused some of the worst famines in history, especially in India and China. Millions of people died because crops failed.
It's hard to even imagine.
It's awful.
But it just goes to show how powerful El Nino can be, right?
It does.
And how connected we all are to these weather patterns that seem so far away.
We really are.
Which I guess kind of makes you wonder, if El Niño's had such a huge impact on us in the past, what's the future hold? Especially with climate change and everything.
That's the big question, isn't it? It's like, how do we prepare for a future where we have both ENSO and climate change to deal with?
Right, exactly. It's almost like trying to predict the weather when the climate itself is changing at the same time. So, like, what can we even do?
Well, I think a good first step is better forecasting. Like, we need to be able to predict El Nino and La Nina more accurately and further in advance.
Okay, that makes sense.
That way, people have more time to prepare, right?
Right, those early warning systems are so important.
Absolutely. They can literally save lives.
Totally. Okay, so better forecasting, that's one thing. But what else can we do beyond that?
Well, forecasting is just the beginning, right?
Right.
We also have to get better at dealing with the impacts of ENSO.
Okay. So, like, what does that look like?
So things like developing sustainable agriculture,
Okay.
investing in better water management, and protecting those vulnerable ecosystems we were talking about, like coral reefs.
Yeah, those are already on the front lines of climate change.
Exactly.
It sounds like we need a lot of innovation.
We do.
And global cooperation, too, if we really want to tackle this. It makes you realize just how much we still don't know about El Nino and how it might change as our climate changes.
That's very true.
Like you were saying earlier, those ENSO variations, the Modoki and the Costero.
Right.
Some scientists think those could become more frequent, more intense.
It's definitely possible.
It's wild to think that we've uncovered so much in this deep dive, but it feels like there are still so many unanswered questions.
Oh, absolutely. There always are in science.
That's true. So where does that leave us? What's the takeaway for our listeners who hopefully are just as fascinated by El Nino now as we are?
Well, I think the biggest takeaway is that understanding ENSO is crucial, especially now with climate change. The more we know, the better prepared we'll be, right?
To adapt and to maybe even find solutions.
Exactly.
I think this deep dive has really opened my eyes to just how powerful and complex El Nino is.
Mine too.
It's not just some random weather event, it's a force of nature that has shaped our planet and our history, and it's going to continue to shape our future.
For sure.
Well, on that note, I think it's time for us to wrap up this deep dive on El Nino, or ENSO as it's more formally known. It's been an incredible journey exploring the science, the impacts, and the history of this fascinating phenomenon. And hopefully you, our listeners, are now as hooked on this topic as we are. So until next time, keep those questions coming and keep exploring the wonders of our amazing planet.
Hey everyone, welcome back. Ready to dive into another historical head-scratcher?
Always up for a good mystery.
This one's a real doozy. The Aztec Sun Stone, you've probably seen it, right? That massive stone disc all carved up. People think calendar, but it's so much weirder than that.
Oh, absolutely. It's like the ultimate example of don't judge a book by its cover,
Yeah.
or, a giant stone disc by its calendar markings.
Exactly. So we're using his Wikipedia page as our jumping off point. Because even just trying to summarize what scholars think it meant is a wild ride.
And it gets at those core questions of how we understand cultures different from our own. What survives, what gets lost, and what we choose to emphasize.
Okay, so picture this. It's 1790, Mexico City. You're just chilling, going about your day.
As one does in 1790s Mexico City.
Right. And bam, you stumble upon this thing. Over 12 feet across, solid basalt, weighs more than a school bus.
I'd be making some offerings to the gods of, please don't let this fall on me at that point.
Seriously. But also, what do you even make of it? Because smack dab in the middle, there's this figure, the Wikipedia calls it the Earth Monster.
No.
But even that's debated. But some say sun god, others something else entirely.
It's like trying to piece together a puzzle where half the pieces are missing and the other half might be from a different puzzle entirely.
And then you've got these 4 squares around it. Each one is supposed to represent a previous era of the world, all ending in pretty epic disasters, like devoured by jaguars, swallowed by the earth. Rough times.
It gives you a sense of how the Aztecs viewed their place in the grand scheme of things. Time wasn't linear, it was cyclical. Destruction was just part of the process.
Right, like even with all their impressive cities and stuff, there was this undercurrent of knowing it could all disappear in an instant. So maybe not the most cheerful worldview, but honest. you know?
Definitely honest. And that's something we'll see reflected again and again in the symbolism of the sunstone. It wasn't just about tracking the days, it was about understanding their place in this vast, often unforgiving cosmos.
And how that shaped their beliefs about everything from leadership to, well, human sacrifice. Yeah, we're going there.
It's almost like they saw these cycles playing out everywhere, right? I mean, we look at nature, we see it too, death and rebirth, seasons changing, but they took it to a whole other level.
Oh, totally. And this is where that whole calendar thing gets even more interesting because it wasn't just about knowing when to plant the corn. It was about understanding the rhythms of creation and destruction on a cosmic scale.
And potentially how to influence them. That's where the idea of sacrifice, as brutal as it was, comes in. It wasn't just about appeasing angry gods, it was about maintaining the balance of the universe.
Right, like giving something back to the forces that controlled everything. So we've got this massive stone covered in carvings that are still being debated, and it might have been a calendar, a religious offering, a symbol of imperial power. Anything else we're missing?
Well, there's that intriguing line in the Wikipedia entry about the sunstone possibly being a Tamala cattle.
The what, Macau?
Tamala cattle. It sounds like something out of Indiana Jones, right? But it was basically a big stone platform used for ritual combat.
Okay, get some gladiator vibes now.
Exactly. And some scholars think the sunstone, with its size and carvings, might have served this purpose too, which, if true, adds a whole other layer to its significance.
So imagine this. You're an Aztec citizen, you're going about your day, you look up, and there it is. This massive stone, maybe even painted in bright colors, potentially stained with, from the sacrifices. Talk about an intimidating sight.
It would have been impossible to ignore. A constant reminder of the power of the gods, the authority of the emperor, and the cyclical nature of life, death, and rebirth that underpinned it all.
And speaking of reminders, it's worth mentioning that the sunstone wasn't one of a kind. The article mentions other sunstones found throughout Mexico.
Right. It's not like they just stumbled upon this one giant rock and said, let's put all our cosmological knowledge on this. It was part of a larger tradition, a shared visual language.
Which makes you wonder how much of that language, how much of their knowledge and beliefs was lost or deliberately destroyed during the conquest.
It's a tragedy, really, and it makes interpreting something like the sunstone even more challenging. We're seeing it through the lens of our own cultural biases, often with limited access to the Aztec perspective.
It's like trying to understand a joke from a culture you know nothing about. You might get the punchline, but you're missing all the nuances.
Exactly. And that's what makes the sunstone so fascinating, also so frustrating. It's a tantalizing glimpse into a lost world, but one that we may never fully understand.
Okay, so we've talked about the sunstone's possible meanings, its potential uses. But what about its rediscovery? Because if I remember correctly, it wasn't just chilling in a museum when the Aztecs were around.
Oh, not at all. This thing was lost for centuries, buried right under Mexico City.
Buried.
Yeah.
Like literally underground.
Literally underground. It wasn't until 1790 that they stumbled upon it again during some construction work. Can you imagine?
Talk about an oh wow moment. But also talk about a headache. Hey, boss, we found a giant stone disc with what looks like a very angry deity on it. Should we keep digging?
I can only imagine the conversations that happened after that discovery.
Seriously.
Yeah.
It's like finding a lost pyramid in your backyard. You'd think something that big would stay lost, but nope, they dug it up.
And it's not like they just brushed it off and put it in a museum. The article says they actually mounted it on the cathedral wall.
Wait, seriously, the cathedral?
Yeah.
After everything,
Yep.
That's a choice.
It really puts things into perspective, doesn't it? I mean, here you have this symbol of Aztec cosmology, maybe even used for rituals, literally overshadowed by the architecture of the colonizers.
Talk about awkward family photos. So they slapped it on the cathedral wall, but eventually they moved it to a museum, which, okay, good, but that kind of brings up another sticky question, doesn't it?
Oh, absolutely. The whole who owns history debate. Is it ethical to display artifacts like the sunstone, often far removed from their original context, for our own education or entertainment?
Right. Like, we're not even sure we're interpreting it correctly. Part of me thinks it should just be back in the ground, left for the Aztecs' descendants to decide. But then again, we'd be missing out on all this fascinating history.
It's a tough one, and there are no easy answers. But that's the thing about history, isn't it? It's messy, it's complicated, and it forces us to confront these uncomfortable truths about the past.
Truths that are still relevant today, too. I mean, the whole debate about cultural appropriation
Yeah.
that's rooted in stuff like this, you know? Who gets to tell the story, who profits from it, who gets to decide what it means.
Exactly. And the Sunstone, for all its mystery and grandeur, is a stark reminder that these debates aren't just academic, they have real-world implications.
So as we wrap up our deep dive into the Aztec Sunstone, I'm kind of left with more questions than answers, but maybe that's okay.
I think so too. Sometimes the best we can do is acknowledge the gaps in our knowledge, approach the past with humility, and keep asking those tough questions.
Exactly. Because who knows what other secrets the Sunstone and objects like it might be hiding. So that's it for this deep dive. Until next time, keep exploring, keep questioning, and remember, history is never truly set in stone.